Alright, so we're in Unit 0, Section 9 on symmetry. The two types of symmetry we're going to study are line symmetry and rotational symmetry. What we're talking about here is we're talking about when figures can be mapped onto themselves. Symmetry is the property of a shape that allows it to be carried onto itself by reflection or rotation. Line symmetry is where we start because we've already seen it when we looked at y equals x squared, the parabolas last week. Parabolas had an axis of symmetry, a line where one side was a mirror image of the other side in the graph. Every point can be mapped onto itself by a line of reflection, so this point is mapped onto another point that's still on our graph. This point is mapped onto another point that's still on the graph. Every point's mirror image is there, creating our axis of symmetry, which is the line of symmetry where what's on the right matches what's on the left. So that's all we're doing, except we're going to think about geometric shapes. So if I could draw a perfect square, would there be lines of reflection? Would there be ways that we could reflect this shape so that every point on one side matches every point on the other? Sure. There'd be lots of ways we could do it. That's what we're going to be thinking about and working on today. Finding line symmetry, thinking about line symmetry, thinking about how shapes can be reflected onto themselves. The other half is rotational symmetry, which is very similar, except we're looking, is there a point inside the figure that we can rotate our figure around and get the same figure back, rotate it onto itself, so that the image is exactly the same as the pre-image. So if we took that square again, and we started rotating around the center of the square, you could rotate your points and definitely have it not match up. But if we kept rotating and got this corner point all the way over to that corner point, wouldn't we then have rotated it so that they did match up? Couldn't we take this corner point and rotate it to that corner point? Or to that corner point? 90 degrees, 180 degrees, and 270 degrees would get us images that map onto itself. And then 360 degrees would get you all the way back to the original figure again. The order of rotation is the number of positions in which a figure can be carried onto itself. Rotating all the way around a circle, and you are order 1, which is really no rotational symmetry at all. So the only way this shape can rotate onto itself is if we take and we go all the way around a circle back to every point going to the same place. We call that order 1, but that has no rotational symmetry because it's just the same figure. The only way you can do it is by mapping it to itself, back to the original position. And then the degree of rotational symmetry is how many degrees around a circle you must carry a shape before it is mapped onto itself. So let's go look at actually using some of this stuff. So here's our parabolas. We know what our parent function is. We know how to shift things. Our x, y here is shifting to each point. The x's are getting +1. The y's are getting +2. We're shifting right 1 and, up 2. So right 1 and up 2. And we shift all of our important points, all 5 of them, so that we know what our parabola looks like. There's no minus sign, so it's not a reflection. The axis of symmetry, that line, x equals +1, that's the line that we're talking about when we're talking about a line of symmetry. Every point on one side maps to every point on the other. So this isn't exactly new all of the time. It's new some of the time. Our domain is all real numbers. Our range, our y's are all greater than 2. So from 2 to infinity. So looking at some geometric shapes, a heart has one line of reflection. You can't put another line in somewhere else because the points wouldn't match up. There's no point for the tip of the heart in the concave part of the heart. So things like the letter A have one line of reflection. Some things can have multiple lines of reflection, multiple ways you can fold it and get everything to map to itself. Triangles, if they're equilateral, have 3 lines of reflection. Lots of things have no lines of reflection, though. But a lot of them still look like they might. And that's the tricky part. The letter Z has no line of reflection. It's not symmetrical through a line. This point can't be reflected over the line and have a buddy that matches up to it. Some things are easier to identify as no line symmetry, like the teardrop on the right. Some things are really hard to identify as no line symmetry, like the parallelogram. Lots of people really have a hard time with the parallelogram having no line symmetry. They want it to be able to fold and match up with itself. It looks like it should, is the usual answer I get from people. So if we need to take some patty paper tomorrow and do a little exploration that you can't actually do that, let me know. That can be one of the activities we try. So pause this. Try this little checkpoint on line symmetry really fast. Shouldn't take you more than a minute. Check your answers real quick. Write down anything we need to talk about when you come to class tomorrow. And we're going to move on to rotational symmetry. So I think this is one of the hard parts about symmetry for most students, is that there's 2 things going on: line symmetry and rotational symmetry. In the rotational symmetry, we want to think about rotating them around the point. For each of the figures below, decide if the figure has rotational symmetry by circling yes or no. Can we rotate it? So now we're not folding it, we're rotating it. So, can you rotate and get the same things out of these is the question, without rotating all the way around a full circle. If we take these points, some of them there's multiple ways to rotate and get the same thing. This one has yes, and I'm not even going to draw all the rotations because you just take it to each one of the possible rotations. So rotational symmetry. It's a very visual effect. Very hard for a lot of people. So there'll be patty paper available in my room. You can always trace any of the figures through the clear patty paper and then turn the patty paper to see if it actually matches up or doesn't match up. That's one hands-on tool that you're allowed to use, even on a test. If it comes to a question with rotational symmetry and you want to just go grab a piece of patty paper from the box of patty paper, I'll be perfectly okay with that. That's using tools correctly. Order of symmetry. So things that can't match up, that have to go all the way around the circle, are called order 1, which is no rotational symmetry. Order 2, when you can take the points and they match up just once and then make the full circle mapping onto itself for 2. That's how you get your order. So order 2 means there's one rotational symmetry before the full circle. So that's the 2 things they're counting. Order 3, 1, 2, and 3 gets you all the way back to the beginning. So there's 2 rotations, and then the third one gets you back to the original figure. Order 4, same way. So pause it, try the checkpoint. So checking these ones is a little tough because there's a couple that weren't drawn very well. 12, I will accept 2 or 4. Depends on whether you see these as being the same or different. If you looked at it and thought they were the same, you'll get 4. If you looked at them and thought they were different, you'll get 2. For 14, it's very similar. Is this a square or a rectangle? Really hard to tell in that one. And for 15, it's the same thing again. Is this longer or shorter or the same as that one? If all the spokes are the same, you should get 8. If those 2 sizes are different, you should get 4. In 16, it's clearly a rectangle, so we don't have that confusion on whether we can go 2 or 4 times around. And then the degree of the rotation. Each one of those rotations going around is of what degree? So when you start and go halfway around, half of 360 is 180. So you start and go 1/4 of the way around, 1/4 of 360 is 90. If you start and go 1/3 of the way around, 1/3 of the way around is 120. If you start and go 1/5 of the way around, 1/5 of 360 is 72. So remember here, all you're really doing is saying, I'm going around 5 times, so 1/5 times 360. How do you multiply a fraction times a whole number? You put the whole number over 1, and then multiplying fractions ain't no problem. Top to the top and bottom to the bottom. So you get 360 divided by 5, and you divide 360 by 5 to get 72. If you're not dividing 360 into 5 on your head, you should have your scratch work. You should actually be doing this, making sure that your number sense is strong by working with the numbers. If you just plug into the calculator, your number sense gets weaker instead of stronger. You want to develop your number sense by using the basic things that you know how to do, even though you don't like to do them. So do long division by hand. Get better at working with numbers. Try the checkpoint. See how you do. Write down any questions, and I will see you tomorrow.